Preparing to go live.
Okay, I can see it's go live. Okay.
It says go live. Good. Okay, I'm going to give you co-host permission, and then I'm going to do a little introduction to you. I'm going to make you co-host, then you can share your screen. Hello out there, if anybody's watching. We are now live. We should be now live online, and it's a great pleasure to welcome all my guests to the Into the Impossible Arthur C. Clarke Center for Human Imagination's Into the Impossible podcast series. This is a subset, a playlist that we have called Brilliant Minds that we're conducting with all sorts of brilliant guests. And I was saying it's not only a pleasure to welcome great scientists of all kinds, but especially when it's a friend, and especially when that friend is also a colleague, and especially when that friend is such an amazing human being, such as Kaixuan, who I'm glad to call a colleague at UCSD. How are you doing, Kaixuan?
Great, I'm doing great. And it has been busy in the past several months, and especially this week.
Yeah.
I think we should share the news with the outside community.
Yeah, it's amazing. Yeah, congratulations on these results. And they've generated not a small amount of interest and controversy even. So I'm hoping that people will enjoy this discussion. I thought I'd start off with a quick highlight of who you are and what you are. So I'm going to share my screen. Oops, I'm going to do it like this. And we welcome people out there. We're just getting started. It's about 10:36 in the West Coast of the United States in California. And I reached out to Kaixuan earlier this week to have a little discussion about these fantastic results, which came out on the 17th, which seems like a month ago, but was really only 2 days ago, as you pointed out on Wednesday. Was released a paper entitled Observation of Excess Electronic Recoil Events in Xenon1T. Now, you might not think that this would set the world on fire, but it's some of the interesting details that are just being cut off at the bottom there about relationship to other exotic things called Axions and so forth. I hope we'll get into all that good stuff. I just want to highlight this slide that I saw that I really enjoy always seeing. All my friends on Xenon1T, including Professor Elena April, who was our Margaret Burbidge visiting scholar this year at UCSD, and Kaixuan helped to bring her to our fine university. UC San Diego has a rich tradition of not only people that are very brilliant minds, but in particular, people have made massive contributions to our understanding of dark matter and other exotic phenomena, including Margaret Burbidge, and that's, of course, the namesake for the professorship that Elena April, the PI of Xenon1T experiment, leads, and she had that position. So it's a great thrill. But of course, it's a great thrill to see Kaixuan up there.
Did you find Elena?
I do. I see her. She's staring right at me. I don't know if you can see my mouse.
She was stuck in the apartment in Brooklyn.
Yeah. Yeah. She's gotten a lot of attention lately, and she's handling it with such graciousness, etc. And she enjoys the spotlight, but I think she also does such a phenomenal job as an ambassador of science and a mentor to people like you and even like me. The brief amount of time I've come to know her, I've just been really honored and blessed to have this great, wonderful, relationship with her. So thank you for bringing her here. I wouldn't have met her otherwise. So I refer people, if you're interested, we did an event with Kaixuan, Elena, and some other folks on the occasion of the Chasing Einstein movie release that we did at UCSD a day before UCSD was effectively locked down. So for coronavirus. So Kaixuan was part of that. And Elena and I did an episode of Into the Impossible also back in March during her same visit. That was actually, I think, a day before her birthday when she turned 29. No, I don't know how old she is, but she's phenomenal. She also has a chunk of, did you know this? She has a piece of dark matter named after her. Are you aware of this?
What kind of dark matter?
It's an asteroid.
Oh, yeah, I know that. Yeah.
Okay, good. So Kaixuan, there he is in the upper left box. I tried to put a little frame around him just to highlight him. And when we brought him to UCSD, I was a huge champion of trying to get him here. What I also like about this slide, it shows all the this is a technical meeting. This isn't like the press release, right? And you see
this
in the
is
back.
technically meeting 1 month ago. We're basically preparing for the next stage called the Xenon1T.
Yeah, I want to learn more about that. Hopefully we can chat more about that. But what I love about this video, this screen capture is, you see all the normal, kinds of faces and different Zoom backgrounds. But then you see people with like a windmill in the background, and then you see some little kids in the background, and you see part of campus. So I just think it's lovely to see that, science is done by human beings, and we have lives and families, and it's a wonderful humanization. So I like that you let off, or your team let off their discussion with that. Here's Kaixuan's homepage at UCSD. It's called the NE Group at UC San Diego. Its subtitle is Your Mission. Your mission in your group that you've developed, your brand, is to explore the nature of dark matter and neutrinos. And I hope we'll talk about all those. And maybe I think you need to revise the web page, the mission statement needs to add Axions, although maybe it is dark matter, maybe it's not, but I want to get into that. There's also links to find out more about his group, because as we know, professors are just the mere figureheads and the kind of rainmakers for these experiments, and all the work is really done by our postdocs, graduate students, and undergraduates. And Kaixuan has the second best at all of UC San Diego. No, I'm just kidding. You guys are phenomenal. I love the fact that you're here in San Diego doing this hardcore research, including, which I hope you'll describe, these really massive detectors. It's impossible from this little cartoon that I stole from your Dropbox slides to really get a handle on this. I will put some resources and links to ways that people can learn more and connect to you after this is done recording. We're going to talk about this. Hopefully you'll walk us through. You have a version, I'm sure, of this type of slide in your presentation. And it's just really cool. We'll nerd out a little bit, but we'll also explain what the meaning is. And perhaps, maybe, I like to get philosophical. I like to think about what are the implications for the grandest questions of the universe, the nature of matter, the origin of matter, and perhaps exotic matter, such as possibly the result of your Wednesday's detection, our announcement. So that's the end of my slides. I'm now going to turn it over to the driver's seat to Kaixuan. And I'm going to go back to the meeting here. Let me see. I'm going to stop sharing. Okay, Kaixuan, are you able to share your slides, sir?
Okay, I'll share my slides, and I hope I don't need to go through all my slides, which was presented by our fantastic graduate student on Wednesday. But I will illustrate some of the results if people are interested. Let me share my screen. All right, can you see it? I will just enlarge that. So Xenon1T is really our current experiment, and it's started from almost 19 years ago when I was a graduate student. At the time, we started with Xenon10, which is just a 10 kilogram of experiment. And as my fun graduate thesis project. And it turns out that the technology we use with a two-phase xenon time positioning chamber really is fantastic for dark matter detection. And ever since we have built a larger and larger detector, including Xenon100, which is a 100 kilogram detector. And then starting 2012, we started prepare this ton scale. This is the first ton scale experiment using liquid xenon time projection chamber for dark matter search. There are other experiments in the world and also ongoing. Our next stage would be Xenon1T, which is being assembled this year, and we expect to start running soon. So that would use a total more than 8 tons of liquid xenon inside. So that's the kind of our research timeline and plan. And the results in these 2 years, in the last few years, are really coming from the Xenon1T, because this lowest background detector, dark matter detector ever built. and not only low background, but also a massive target with total 2 ton in the sensitive target. And we usually use the 1 ton, about 1 ton in the innermost, the cleanest part for dark matter search. And I'm not going to talk about dark matter search today because our result is really actually not about dark matter, but related. But Xenon1T has set the most constrained limit on WIMP dark matter. For any dark matter above 3 GeV, which is 3 times the mass of protons, Xenon1T has the most constraining limit, up to a few TeV or even higher. So we were a little bit kind of sad, we didn't see any signature of dark matter after almost 20 years of looking and a lot of people's effort, not only including our collaboration, but also including people from all around the world, in the US, in Europe, in Asia, in China, Japan. And it really took a lot of effort. But I mean, for experiments like such a big scale, although we didn't see any signature of dark matter, there's some surprise from time to time, especially this time. And let me just bring to there's a picture of Xenon1T inside the detector. This is actually my background. So Brian Keating, you have a background of your mountain in Chile, right?
That's right. That is right.
So I don't have a mountain picture of underground, but this is our underground experimental device. If you ever visit Gran Sasso underground lab in Italy, you will see this very beautiful window building and with all our instruments inside. Anyone can go there and just take pictures and share the joy. The detector that I mentioned just earlier, the 1-ton detector, is shown actually inside on the left side. I don't know how do I show my
your cursor. I think if you go to one of these tools, it should maybe give you a toolbar on the screen share. Let's see, annotate.
Annotate.
I don't know if you could do that. So I'm drawing.
Okay.
Do you see it?
Yeah. Can you
hold
see
down the cursor?
Hold down cursor. Can
I see your cursor. Yeah.
Okay.
Yep.
Cool.
You see it.
Okay.
So let me clear the. I'm going to erase my drawing there. There you go. Oops,
so
okay.
I use this way. You can see my mouse, right?
Yeah.
So this is the Xenon1T detector actually, and it's inside a 10-meter diameter water tank, which in the underground side is already a lot of cosmic muon has already been shielded, but there's additional background from the rocks or whatever outside of the detector. So we use a big water tank to shield additional background, and the 1-ton detector really hiding in the innermost part, really clean and quiet. Okay, and all the other instruments is from the outside to instrument to get signals out of it, and from an array of PMTs. As you see, there's a photo multiply tubes inside the Xenon1T detector, looking from the top and from the bottom, and we take all the signals from these PMTs to a data acquisition system, and then transferred all around the world, and our people will access the data and analyze the data. So basically, we can actually do the analysis like even we are locked at home, we can do the analysis and we can look at all the signals from our data. So I'm not going to give the details of how these signals are generated. I think it's very complicated, but if anyone's interested, I can answer the questions. Basically, a particle just get into our detector would create a scintillation, we call S1 signal, and also create ionization, we call it S2. However, dark matter not only interact very rarely, but the energy deposit is also very small. So basically, we have to amplify this ionization signal in order to have a clear detection.
So any kind of particle can come in, smash a xenon atom, ionize it, and liberate electrons, and then you directly detect those electrons, which are an indirect signature of some kind of particle, possibly dark matter, etc., or it could be a background that is responsible for the ionization due to its kinetic energy.
Yeah, due to kinetic or other interactions. So any kind of particles, including the background, can interact in the one-ton detector, produce this kind of S1 and S2 signals, we call. And we use this S1, S2 signal information, we can get the three-dimensional position where this event happened in our detector, and also the energy of this any event interacting our detector. And in addition, we use the information between S1 and S2 to tell what kind of particles actually they are. So whether it's a neutron or a gamma ray or electron or dark matter or neutrinos. So really getting from this S1, S2 signals. So for each event record registered in our detector, we have a few hertz of event rate. Most of them are background, we know, but maybe the one out of a year, maybe we see a dark matter. That's the difficulty of the experiment.
So the S1 signal is from the cylindrical walls, effectively, or is it? So SS2 is the end caps, right? The top end cap or the bottom end cap.
So S1 is the direct scintillation. So when a particle excites the xenon atom, the xenon atom will produce the scintillation immediately. So this gives a kind of a start of this event.
Yes.
Now at the same time, it produces electrons. The electrons, you cannot see it immediately, but we have electric field applied in the detector. So that's why it's called time projection chamber. So this electron will slowly drift up, and then on the top, there is a gas phase. And there is a very strong field in the gas phase. The reason is that we want to amplify these electron signals into additional proportional scintillation or electroluminescence. So you turn this electron, maybe sometimes only a few electrons, into light signals. Because the photomultiplier tubes on the top and bottom of the array can only detect light signals. They cannot detect electron signals. And so both S1 and S2 are registered in by these photomultiplier tubes, many of them.
Yes.
Right. So you see these events happening everywhere in a detector. And then this scintillation light will travel inside the detectors and eventually hit by these PMTs and taken out by our data acquisition.
Awesome.
Right. I hope this give you some idea how the detector works. It's not so difficult once you understand. Every time a student come to my office who want to do research with me, I would give them a paper about instrument paper and let them to read it. And next week they come and I ask the student to tell me what's the principle of a detector. And most of them will just get it quickly, after reading our paper and understand how it works. And the rest is just, if you do data analysis, just to deal with this S1, S2 signals, how to get information out of it.
Exactly.
Right. So indeed, it's not so difficult to get into our research. But to build a detector, it took years of effort. And we have a large team of 160 scientists around the world, many of them working on the hardware. They may not look at the data, but they make sure the hardware is being perfectly made. And so we can have a sensitive dark matter search. Now, I want to point you to this picture, which is showing the two signals called S1 and S2. And there are particularly two populations One is called nuclear recoils, one is called electron recoils. Dark matter, heavy dark matter like ring, they would not produce electron recoils, but they would collide with the nucleus and produce a nuclear recoil. So if dark matter happens in our detector, they will appear in this red region. That's what we searched in the past few years to look for the dark matter interaction in Xenon1T, and we didn't find any, or didn't find any convincing evidence they are there. So basically, we look at some signals and in this region, and there are a few events, and some of them look like a dark matter, but more likely a background, say, from neutron and from even from leakage of the top electron recoil band. And in this week's announcement, what we actually announced is the search for some other signals in the electron recoil. We basically on the top band in this green band region. You see there are many events. So this is the plot actually shows our the science data, science search data. So it's not a calibration. So it's a real every event during the dark matter search run what we registered. And you see there are many of these events in this top green band electron recoils. And most of them, we understand they are from our background. And so in this particular search, it's really challenging things to try to understand all the background that can contribute to these green band, all the events in the green band. And that took a lot of effort of our graduate students and postdocs. So by doing that, I would like to show one of the slides of turn this green band into a one-dimensional plot in energy. That is here, yes. So this energy is reconstructed from this S1, S2 signals. And you see it in keV. keV is kilo electron volt. That's the energy of each event deposited in our detector. That's electron recoils.
Got it.
And the vertical the axis is event rate, basically how many events we recorded in one time year. So we didn't see many events, only like a 60 something events per ton year per keV bin. The red one is our expect background, taking into all the known background. And you see on the higher energy, above 10 keV, the data points fluctuate up and down, but more or less consistent with the data. But below 7 keV, there is a strange excess that show up. It's more than the background model can predict. So that excess really calls our attention during the analysis where they are coming from. And if you just count the number of events, the region between 1 to 7 keV, we expect 232 events out of the total period of our search. And we observed 285 events. So that's like 53 more events observed out of 232 background.
What about the event in the bin at 17.5 keV? That's like
this bin?
Yeah, it's like 2 or 3 sigma low, right?
Oh yeah, you have a good eye to catch.
Well, I'm just used to other people picking apart my results, so I can't resist.
Right. So this single bin is actually, it's just a fluctuation. It depends on how you bin this data. If you move the bin, by a little bit, this event, this bin would move a little bit up, and then it will move it down. So this single bin excess, if you take just this bin, well, it's like more than 3 sigma of fluctuation. But if you move the bin a little bit around, then it can shrink to below 2 sigma. So that didn't call much of our attention. The low energy one is not a single bin. You see consistently the events is moving up by after 7 keV. So that you cannot make this fluctuation by just binning them differently.
Yes, I see.
So there's so many bins just show up. So if it's single bin, I wouldn't pay too much attention, but we understand it.
And the other thing, Kaixuan, before, I mean, this is a little bit nerdy and I want to keep it a little bit higher level, but I can't resist. So if you look at the first, 7 or 8 bins, they have this 1 over energy fall off, at least until they bottom out at around 10 to 12 keV. We have fluctuations that are called 1 over F fluctuations, 1 over frequency, basically meaning if you wait long enough, things will happen, and there's a preponderance of long time scale fluctuations in our time order data. Does the same phenomena happen in high energy, in these types, where you have just a preponderance, a huge amount of low energy data compared to high energy data, and then it flattens out to sort of a flat white noise, if you will, distribution, or is that just not relevant?
You mean this part around 10 keV?
Yeah. Or from the lowest, the second bin at 2 keV all the way down to here. Yeah, there's sort of a trend in energy space. Is that a 1 over F? Just an excess of low energy. Of course, the lowest bin is low, much lower, obviously down here at 1 or 2. Is that a phenomenon that you guys look for, or no?
Right. So our detector always have a so-called threshold, right? If you go to lower energy, it's harder and harder to detect. So you eventually would see something the fall off. That's the detector threshold effect. So this red curve has already taken into account the detector threshold effect, the so-called efficiency. And the events here that show us we really do not expect the background that's going when we go down to the energy, the background should not move up. The background mainly is from, I want to show you the background.
Yeah.
Was the main background, right? That's the one we want to look at. The main background is coming from a radioactive contaminants in our detector called the radon. Radon, you have your radon in your basement. And we also have a tiny amount of radon in our liquid xenon detector. And this radon would produce actually a beta decay from lead-214. So this lead-214 is a beta decay, is one of the daughter in the radon decay chain. And this beta decay would produce a kind of flat background. As you're seeing here, this blue line is the radon. Okay, from 0 to up to 200 keV. It's all more or less flat. Eventually, it will fall down at its endpoint. But at the low energy part, it should be more or less flat, and it should not go up. This radon is our main internal background. Now, back to your question, whether in the low energy will show this kind of detector effect. Well, we do not expect that from our background.
I see.
There are other type of background, for example, like this green, the orange one is krypton 85. Krypton is also a noble gas. Krypton 85, is in the atmosphere from all the past nuclear tests, and we have a little bit amount of krypton there, and we took a lot of effort to build a distillation column to remove this krypton, and the background is subdominant compared to the lead-214. And there are other background. We have all taken all this background into account, even including solar neutrinos that we talk about. I'm interested in neutrinos as well.
Yeah.
And solar neutrinos will not be shielded by the 1.4 kilometer rock of Gran Sasso. It will just enter into our detector. But the rate is still so low compared to other background at this moment. Our next generation experiment would be able to observe solar neutrinos that we can study the neutrinos from the sun.
Yep.
Okay, so after looking this, seeing this excess event, it's a 3.5 sigma fluctuation, and we want to see where they are coming from. And of course, we would not think about something exotic, right? We want to look at something maybe standard model or another contamination background that we we didn't include it in our standard background.
Right.
And that is called tritium.
Yes.
Tritium is one of the hydrogen isotope, and it has a beta decay, and it also has a beta decay, and of about 12 years of half-life. And this tritium beta decay would produce a spectrum that can explain the excess. So if you look at this plot, the red one is after we put tritium into the consideration to fit our data. And tritium is favored at over background only at 3.2 sigma. The amount of tritium in order to explain this excess is really tiny. It's because 10 to the negative 25 more per more. In other words, I think even put the analogy like few than 3 trillion atoms per kilogram xenon. So that tiny contamination of tritium is not being measured. In principle, there's no instrument can measure such a tiny amount of tritium. We did an estimation using all the arguments we know, including cosmic Janet activation of xenon that produce tritium. But tritium can also be removed by our distillation column that remove the krypton. And tritium will be further removed by our purification system that we use a purification system to remove oxygen, water, all the contaminants down to a very low level, and the tritium will as well be removed. And by estimation, we would expect that if, from all the theoretical calculation, Monte Carlo, we would expect that tritium would be, if, all the arguments are correct, it should be 100 times lower even than this value. So basically, tritium cannot be excluded as a possibility, but it cannot, we also cannot confirm that's coming from tritium. So that trigger us to think about some exotic possibilities, including the solar axions.
Can I ask for one question now, which is, this isn't the first claim by a dark matter experiment operating in Gran Sasso, even of a detection of something which potentially has these groundbreaking ramifications for physics. I'm speaking of the Dama experiment now, which claims many dozens of sigma evidence for the existence of a signal that they claim, although they're really not believed by many people in the high energy astroparticle physicists and dark matter hunter community, as I understand it. I'm not in that community, but how would this signal manifest itself, assuming, before we go on to solar axions and things like that, how would it manifest itself over time? Would there be an annual variation of the kind that Dama has reported with extremely high significance over the last 20 years? With this signal, with the Xenon1T signal, if you just kept operating for a decade, would you see 10 cycles of any sort of periodic event?
So if it's tritium, it should not have an annual cycle. Tritium would decay over time, so you would see them decaying over the 10 years of half-life. So that can be confirmed if we run a detect for 10 years. So Xenon1T actually is already stopped. We are preparing for our next stage, Xenon1T, which will have even lower background that we can tell whether it's from tritium or from other exotic particles. Now, the signal Dama observed actually is much higher than what we observe here. So many orders magnitude of rate higher than what we have here. So it's completely different story. However, we also want to mention here what we observe, the excess is real, more than 50 events more than we accept background. So whether this 50-something events coming from a background or from some new physics, that needs to be examined. So tritium is just one of the background that we considered, one of the additional background we consider. And it seems the amount cannot really explain what we observe, but we also cannot really confidently reject this hypothesis. There might be other background, as you may heard from our press release. There is a possibility of argon-37, but from my naive calculation, argon-37, if it's tiny amount from the air leaked into our detector, they would destroy our S1, S2 signals completely. So I would like to invite all the experimental colleagues from the world to see what are the possibility of the background before we claim anything. But it's intriguing also to consider it as a signal from solar axions.
And is the data, are the data available that someone could actually do that?
Do what?
Oops. Look for alternative explanations using actual Xenon data. Is there a way that we, in our community, we publish maps or we publish power spectra, et cetera? Are the data available, or are they still proprietary to the Xenon collaboration?
So data, whatever we publish here are the data we have. I'm just thinking if there's any other exotic background that we can use the similar statistical test to check them. And the people can also use our public data, released together with a paper to check the possibility just by fitting on our spectrum to see whether the kind of hypothesis background can fit into the fluctuation of our data as well.
Interesting. Okay, great.
Yeah. In nevertheless, whatever background, the amount is so tiny that it's really difficult to explain.
Got it.
Right.
Great.
So with this in mind, we look into the possibility of solar axion. And solar axions is produced by the sun, by the way. And if we fit, so there are three components. I don't want to go into details of what kind of, these three components, there are three mechanisms to produce the axions by the sun. And but in our detector, we can see all the three components by detecting the solar axion, so-called axial electric effect. That axion will be absorbed by the xenon atom, and an electron is ejected. So basically, we are looking into this electron recoil signals to look for these solar axions. And if we fit all these spectrons together with our data, with our background with our data points. Now, this is the spectrum. The red is a spectrum included the axions. And this axion is favored of the background at 3.5 sigma.
Are there any fine-tuning parameters? Are there any parameters that have to be tuned, or
so
in order to get, or is it rigidly fixed by?
So yeah, maybe I better, if we have time, we can look at a little bit about axions. So axions produced by the sun by the three processes, mostly governing axion interaction with the electron, axion interaction with the photon, and axion interaction with the nucleons. And they would produce this kind of, three processes produce different kind of spectrums. The ABC process would produce more dominant at the low energy. The primal cuff, that axion photon coupling, would produce this purple spectrum, and the axion nucleon coupling would produce this monoenergetic peak. And the rate of the three process can vary depending on the coupling. So we just plot in the same plot so you can see, but the rate can go up and down. And we fit them into our data just by varying the couplings and see if our data can explain it. So our detector has some resolution. So eventually, if you're taking our detection efficiency and reconstructing resolution, then you would expect the signals, three components would like that. And there are some bumps, the curves, the dips, compared to trillion is really a kind of is a smooth curve going down. But here there are some curvatures. So that makes some difference of the data fitting. for the solar axion. And if you look at data, when I saw this, it looks like there's a dip, there is a bump, but of course, we have to rely on the statistical test to make a quantitative analysis. And this 3.5 sigma is more favored compared to the Trillian hypothesis of 3.2 sigma. That I think that caused the excitement of the possibility of this is really coming from the solar axions instead of a background. But we really cannot claim that we have detected that solar axion. Eventually, we need a 5 sigma of significance in order to claim a detection. And that has to rely on our next generation detector, Xenon1T.
I see.
Right. Yeah. So I want also mention, if we take this fitting and then put into the couplings of the axion, what could it be for, right? And this is one of the GAE is the coupling of axion to electron. GA gamma is an axion to photon, and the Xenon1T work would in this blue region. Okay. I want to say, there are other experiments specifically searching for solar axion like CAST, and the CAST has set a very strong limit on the GA gamma, the axion photon coupling, and anything above this green line has been excluded. But below this line is still valid. But in our case, this is a GAE, the electron coupling, is quite different intention with this so-called stellar cooling. If the sun can emit axion, the stars can also emit axion, and that by the estimation from the stellar cooling, we can estimate what amount of kind of coupling that require that the energy loss of the stars. And this is from astrophysics analysis. And I got questions from my astrophysics colleagues say, oh, this is in tension with the Xenon1T. Your coupling is too large.
Right.
And there's also almost 1 order of magnitude, right? So, I'm a particle physicist. I want to learn more about astrophysics, what actually caused this tension. Maybe our result is really not axion, but maybe there is also astrophysics process that can cause such a 1 order of magnitude difference. So I think that's interesting to think about the possibility of the astrophysics and look into the calculations. But I'm open to, I still would rely on our experiment, the next generation to say more about the direct evidence of axion electron coupling.
Very interesting. So yeah, I think the topic people have been most curious about is, these results from these cooling experiments. And I'm not an expert, not all astrophysicists are knowledgeable about all different types of limits, but this is certainly, I think, the most kind of interesting. And as Richard Feynman once said, the first principle of being a scientist is you must not fool yourself, and the realization that we have to have is that we're the easiest to fool, and that if you always think that way, it really translates, as you described, into not trusting your own results, and really not trusting them that you didn't make a mistake, but that the explanation that you want, or in your heart of hearts you'd most like to be true, is has to be the final hypothesis. It has to survive the test of all possible other sources, including backgrounds, including contaminants, and so forth. So I was wondering, in the future, you said you can't directly measure the tritium, and that's sort of the most prosaic explanation on Earth, at least, for background. But on second thought, why not get 100 liters of tritium, liquid tritium, and do an experiment? I mean, first of all, I think that would cost more than the GDP of the planet. But are there other ways to go after tritium, and are there other ways to possibly do a detection that could remove what we call a systematic error, potential source of systematic error, and or calibrate the instrument better? In other words, how much energy are you going to put into better calibration versus bigger fiducial volume?
So for tritium, actually, tritium has been used for calibrating the xenon detectors. We didn't use it for Xenon1T, but I had a test in Xenon100, our previous generation detector, at the end of the Xenon100. And also in the Lux experiment has used the tritium for calibrating the detector. So we really understand the tritium spectrum well, how it performs in the xenon detector. But Xenon1T, we didn't use tritium at all for calibration. And if a tiny amount of tritium, where they're coming from, there's still a puzzle. When I talk about the next generation, is really the Xenon1T, and we expect the background will be lowered by a factor of 6 compared to Xenon1T. So that means that the background, the flat background, would be further suppressed. Then if it's tritium, you would see them much better. And if it's also axion, then you would see this spectrum better. That's why we say with the Xenon1T, we would be able to have better discrimination between the tritium hypothesis and the solar axion hypothesis with a lower background.
I see.
I think that's the only way from experimentally, how do we disentangle these two hypotheses. So it will not be 10 years away. I hope in the next year we would be able to say something of this.
So you think, okay. And so tell us, so NT, what does that stand for? It's not 9 tons, because I think you're only using
10 ton
8.
in total inside this time projection chamber is 6 ton, compared to the 2 ton of sensor target of Xenon1T. So it's like 3 times the active volume. And so this N, we can replace it with a 6, but it has been calling N because we are struggling to get more Xenon, more funding to fit the detectors. So in the beginning, this N is uncertain, but now everybody knows Xenon1T, so we just give it a name.
So I have, thanks. I have some questions from the audience. One is, could there be such a thing as a axion or perhaps a dark matter planet? Could there be, condensed bodies in which these objects exist?
I think I have some colleagues that they have some, paper about axion stars, and that's an interesting thing to look at. And I really have no clue. I have very limited knowledge about this. But if you search axion stars, there's some paper you can look at. It's an interesting idea.
And there are some, including Eric Weinstein, who's been on my podcast a lot lately. He has some thoughts about whether or not dark matter could be a manifestation, perhaps, of extra dimensionality or higher dimensions, so forth. What do you make of that? That it may be signatures of alternative, some call it parallel universes, but let's just say extra dimensions that are maybe compactified, extremely small, but it manifests themselves over via modification of gravitational force on scales relevant for experiments like this.
I think certainly there is a possibility. Yeah, and what we are looking for now, the dark matter, is in this 3-dimensional universe that has in some other models called supersymmetry, that would produce such kind of cold relics from the other universe. And but there are other models think about it that may coming from actual dimensions, and there are possibilities, and there are some models that we can test. But first we have to see an excess in our data. Then we can examine all these kind of possibilities.
And just briefly, because I don't often get the chance to interview my friends and coworkers here in a forum such as this, but about a year ago, you had a result on Xenon itself. Can you talk? I believe that's right, correct?
Oh yeah, we did have a result a year ago about observing the rarest decays ever directly measured in the Xenon1T. That's called double electron capture of isotope called Xenon124 in our detector. Now, this is not exotic physics. It's a standard model process but really the decay lifetime is much billions of times of the age of universe. And that it turns out our low background will be able to find that signature. Well, double electron capture, that observation is interesting. It's challenging, but it's not as interesting as another process called a neutrinoless double beta decay. Well, neutrinoless double beta decay would eventually help us to understand the nature of neutrinos, whether it's a Majorana particle or Dirac particle, and what's the absolute mass of neutrinos. And these things are really in the heart of my interest.
Very good. Well, I know you've got a lot of things to get to. It's been a busy week for you, much deserved. Congratulations on your phenomenal work of you and your team, and especially all our Tritons out there who are working so hard. Can you tell people how to find out more about you on the web and on Twitter and elsewhere?
Oh, I see. I have a Twitter account. Sometimes I share my own opinion about results. But if you want to find more about Xenon1T experiment, it's easy, Xenon1T.org. That's the website you look for. You can also find the Xenon Twitter account on Facebook, Twitter, Instagram. Our new generation of student postdocs, they are really good at tell the best story from our experiment. So just search for Xenon experiment in Google, then you'll find all of them.
That's great. Well, Kaixuan, it's a pleasure to call you a friend and a colleague here at UC San Diego. We have the best scientists, in my opinion, in the world that work here. And I'm a little bit biased. But thank you so much for sharing so much of your valuable time. And I look forward to many more exciting results to come from you and your stellar team. Thank you, Kaixuan.
Thank you. I look forward to meet you on campus soon.
Yes, hopefully it will be soon. But this is the next best thing. Thanks, Kaixuan. Have a wonderful weekend. Happy Father's Day, too, by the way. Early Father's Day.
Thank you. Yeah, I'm a father, and you are a father of more than.
Yes, that's right. More tonnage of kids. For now, maybe, who knows. Kaixuan, have a wonderful day. Thank you so much.
Bye-bye. You too. Thank you. Bye.